In this video, we introduce our work towards LiDAR registration with visual foundation models. Let's begin by exploring the core idea behind our approach. Imagine we are given a LiDAR scan and also have access to a surrounding RGB camera. This is a setup commonly seen in many mobile robotic systems. Our method involves feeding the surround view image into a frozen Dino V2 model, from which we extract image features that serve as point descriptors for the LiDAR scan. This process can be performed online during test time, but it can also be applied during the mapping phase, resulting in a 3D map with associated point descriptors. By establishing correspondences between these descriptors, we can perform scan-to-map registration using traditional techniques such as ransack. Let's take a moment to review the key properties of Dino V2 that motivate our work. First, Dino V2 has been demonstrated to generalize effectively across a wide range of domains and camera models. Additionally, it generates highly descriptive semantic features, which can be interpreted as soft semantic labels. These capabilities have led to a broad array of applications, including reliable pixel correspondence matching, even between images with different styles. In our work, we build on this property by applying it to the task of 3D point matching. Going back to our technical approach, suppose we are given the aforementioned LiDAR scan along with surround view image data. Feeding the image data through a Dino V2 model results in pixel feature maps. Using a straightforward 3D to 2D projection, we transfer these image features to the LiDAR scan, producing point-wise descriptors. During localization, we assume that the 3D map has been processed in the same manner. For each point in the LiDAR scan, we compute the cosine similarity with all points in the map. Thanks to aggressive downsampling and an efficient search algorithm, this process is performed in minimal time. For each point, we retain the connection to the map point with the highest cosine similarity, provided it exceeds a defined threshold. These point-to-point correspondences are then used in a traditional outlier rejection scheme, such as ransack, to achieve a coarse registration, which is further refined with point-to-point ICP. To conclude, our main contribution lies in demonstrating that Dino V2 features can be effectively used as point descriptors for scan-to-map registration. Our method offers the advantage of not requiring in-domain retraining, unlike many previous learning-based approaches. Additionally, it is agnostic to the density and shape of the point cloud, making it highly versatile. In our paper, we make 3 claims. First, coupling the proposed descriptors with traditional registration algorithms facilitates robust 3D localization. Second, although simple, our method substantially outperforms more complex baselines. And finally, our approach is robust to temporal changes in the environment. To evaluate our approach, we use 2 long-term datasets, NCLT and Oxford RobotCar. The NCLT dataset spans 1.3 years of recordings across different seasons, but it includes only a few dynamic objects. In contrast, the RobotCar dataset covers 1.5 weeks of data, captures a range of weather conditions, and includes numerous dynamic objects. In this video, we present results on NCLT. For RobotCar, we kindly refer to the paper. In our initial experiment, we evaluate our first and second claims. On this slide, we report the mean translation and rotation errors for registering a LiDAR scan to a 3D map using 3-point ransack. The point correspondences are based on the listed point descriptors. While we provide a more detailed analysis in the paper, the key takeaway here is that our proposed descriptor is the only one enabling robust and accurate scan-to-map registration. To support our third claim, we simulate temporal structural changes in the environment by modifying the 3D maps. Specifically, we remove trees from the map. First, we query all points with tree-like descriptors. Second, we cluster these points to obtain individual trees. And finally, we randomly remove some trees from the map. In this plot, we show the registration recall after refinement for our method, labeled as Dino V2, alongside the 2 best-performing baselines. The main insight is that our proposed point descriptors are robust, even when faced with significant structural changes in the environment. To conclude, we have shown that Dino V2-based point descriptors can be effectively integrated with traditional registration algorithms, resulting in robust point correspondences. Thank you for your attention.